Hello. Today we're going to talk about Chapter 21, comparing two proportions. So comparisons between two percentages are much more common than questions about isolated percentages, and they're a lot more interesting. They're often used to know how two groups differ, whether a treatment is better than a placebo, whether this year's results are better than last year's. Those are your typical types of questions. This is a common example here of comparing two proportions. And so that's what we're going to learn today, is how to solve a problem like this. So in order to examine the difference between the two proportions, we need another ruler which deals with the standard deviation. All right. So recall that the standard deviations don't add. We can't just add those, but we can with the variances. Okay, so the variance of the sum or difference of two independent random quantities is the sum of their individual variances. Okay, so it doesn't matter if we do adding or subtracting, we're always going to add the individual variances. So to see it as a formula, okay, that would be here. So proportions observed in independent random samples are independent. Okay, thus we can add their variances. So here's your standard deviation, okay, and thus this is the standard error. Okay, same idea. All right, so let's do an example. So a survey of 886 randomly selected teenagers found that more than half of them have online profiles. There appear to be differences between boys and girls in their online behavior. So among the teens, 57% of the boys had online profiles compared to 70% of the girls. So if we want to estimate how large that difference truly is, we're going to calculate the standard error. So how we do that? Okay. All right, since the boys and girls were selected at random, okay, it's reasonable to assume that their behaviors are independent. Okay, so here we have our standard error of the boys. All right. 57% have online profiles, 43% don't, total 248, take the square root. Standard error of girls, 70% have online profiles, 30% don't, over a total of 256. Now to do the standard error of the difference, you add the variances, so you put those squares back on, and then take the square root. Okay, so that's what that means. So, of course, with any test, we have assumptions and conditions. So we have our independent assumptions, your randomization condition. The data in each group should be drawn independently and at random. Okay, so it's all got to be randomized. All right, that's important. 10% condition, got to have, shouldn't exceed 10% of the population. And the two groups we're comparing must be independent of each other. That's very important. Okay, so you can't do, look at a student's pre-test and their post-test. Okay, you can't compare the results of individual people from like one trial and then the same people in the second trial. They have to be independent. Okay. Sample size condition, each of the groups must be big enough. Okay, so success failure condition, so they have to have at least 10 successes and at least 10 failures observed in each. All right, let's do another example. So among a random sample of teens aged 15 to 17, we've done this one before. Well, can we use these results to make inferences about all teenagers or all 15 to 17-year-olds? So what are the assumptions and conditions? So let's go through them. Randomization. The sample of boys and the sample of girls were chosen randomly. Okay, they even said it in there. 10% condition. All right. The number of boys and girls total are each less than 10% of the total population. Independent groups assumption. Because they were selected at random, it's reasonable to assume that the boys' behavior are independent of the girls' behavior. Okay. Success failure condition. So you multiply the number of kids times the success and failure of each. We got over 10 on all of them. And so because all these assumptions and conditions are satisfied, it's okay to proceed with inference for the difference in proportions. So now we can keep going. All right, so we already know that for large enough samples, each of our proportions has an approximately normal sampling distribution. The same is true of their difference. So provided that the sampled values are independent, the samples are independent, and the sample sizes are large enough, the sampling distribution is modeled by a normal model. So here's your mean, and here's your standard error. Or I'm sorry, your standard deviation. All right, so when the conditions are met, we are ready to find the confidence interval for the difference of two proportions. So that's called a two-proportion z-interval. So the confidence interval is this, all right, with the standard error being this. The critical value depends on the particular confidence level. We know that like as, a 90% confidence interval, for example. So let's do an example. So going back to the online profiles, let's construct a 95% confidence interval for the online behavior. So here we follow the formula. The percentage of girls minus the probability for boys. Okay. Again, we're following the standard error here, girls minus boys. It says it right here. So then we do plus or minus the z-score for 95% confidence interval. And then our value here we got on that last slide. And then we add them up, add and subtract. So we can be 95% confident that among teens, the proportion of girls who post online profiles is between 4 to 21 percentage points higher than the proportion of boys. So it would seem that yes, girls are more likely to post profiles than boys of the same age. Okay, that's a pretty big difference. All right, let's do another example, but this time we're going to do it on our calculator. So this one asked whether they attribute intelligent applied to men in general. So what did men and women think about that? So we can go to our calculator. Let me pull that up. We want to go to Stat, Tests, go down to 2 proportion z-interval. Now, the number for x, we would do 0.28 times 506. All right, the number of men times the percentage of those men that agreed. Well, we're not going to say that the number of men was a decimal. That doesn't make sense. So that's why we round to 142. That's why I put that over here. There was a total of 506 men. Then for the women, it was 14% of 250. So when we do that, we get, whoa, did I not do that right? 14% of 250. Okay, there was a typo. I said 250. That was supposed to be 520. Silly me. So when you multiply it, you get 72.8, but we round up, so 73 people. Okay, we want to make sure we have enough people. And then, let's see, that total was 520, and we want a confidence interval of 0.95. So then we calculate, and there's our interval. So we are 95% confident that the proportion of men who think the attribute intelligent describes males in general is between 9 to 19 percentage points higher than the proportion of women who think so. Again, because we did the men first and then the women second, we did men minus women. So that positive difference, okay, is showing that men would have a higher percentage. Okay? All right, keep that in mind. Make sure you know how to interpret that. All right, so let's do another example to make sure we can understand confidence intervals. Okay, so read this, pause it. That way you don't have to listen to me keep talking. All right, so we want to know if there's a difference, okay, from emails and those requests by regular mail. Okay, so they found this confidence interval. So what does that mean in context? So hopefully you got this. We're 90% confident that if members are contacted by email, the donation rate will be 4 to 18 percentage points higher than if they received regular mail. All right, now again, look at the percentage. You've got it higher from email than you do those from regular mail. So since we've got a positive change here, or positive percentage, or difference, the bigger one's going to go first. Okay, so based on that confidence interval, what conclusion could you reach? All right, if we tested the hypothesis that there's no difference in the response rates. Okay, well, the difference should be 0, right? If we're looking for no difference, then 0 should be in my interval, but it's not. It's between 4 and 18 percentage points. So that's stating that there's a difference, so we'd reject the null hypothesis. Okay, you got to know how to describe your confidence interval and where to go from there, okay, and what that means. All right, so now let's talk about hypothesis, or hypothesis testing. So the difference in your null hypothesis is just going to be P1 minus P2 equals 0, right? That's what you're trying to state in your null hypothesis. Since we are hypothesizing that there is no difference between the two proportions, that means that the standard deviations are the same. Since this is the case, we're going to pool the counts together to get one overall proportion. Okay? All right? So I literally mean throw them all together. So you get a pooled proportion, your success for the first batch, your success for the other batch, over the total for one plus the total of the other one. Okay? You're literally throwing it all together. If the numbers of successes are not whole numbers, round them first. This is the only time you should round values in the middle of a calculation. The only time. Okay? I know that's weird. I always tell you, save all those crazy decimals. But this is the only time I want you to round. Okay? To whole numbers. Okay? Because we're supposed to have counts. These are counts. Okay? We then put the pooled value into the formula, substituting it for both sample proportions and the standard error formula. Okay? Throw them all in there. Hopefully this is making sense. Okay, so we can reject our null hypothesis if we see a large enough difference in the two proportions, right? Because again, our null hypothesis was that the difference is 0. So how can we decide whether that difference we see is large? Well, you compare it with the standard deviation. And unlike previous hypothesis testing situations, the null hypothesis doesn't provide a standard deviation. So we'll use a standard error. So in this case, pooled. The conditions for the two proportion z-test are the same as for the two proportion z interval. Okay, what we just did. We are so here we're testing the hypothesis that the difference is 0. Okay, or equivalently that the differences are the same. Not the differences, that the proportions are the same. Because we hypothesis that the proportions are equal, we pool them to find the pooled proportion. Okay? We then use the pooled value, okay, to estimate the standard error. So notice the pooled values are what used on top. We still use the different counts, okay, the totals for the different sets of data that you're comparing, but the pooled goes on top. Okay, so this is for a z-test, two proportion z-test. And then we find the test statistic. So when the conditions are met and the null hypothesis is true, this statistic follows the standard normal model, so we can use that model to obtain a p-value. Okay, it's always easier with an example, so let's do an example. So let's talk about those that snore. So people under 30 and people over 30. Use a two proportion z-test to determine if there really is a difference between the two age groups. All right, so state the null hypothesis, the alternative hypothesis, All right, the two groups are independent of each other because the sample was selected at random. All right, independence assumption. The National Sleep Foundation selected respondents at random. They set it in there. Okay, so they should be independent. Randomization condition. The respondents were randomly selected by telephone number and stratified by sex and religion. Ooh, did I not put all that info? Yeah, I didn't put all that info. It's in the textbook, right? Okay. I didn't just make this up. It's in the full detail. Okay. 10% condition. The number of adults surveyed in each group is certainly far less than 10% of the population. Okay. Yeah. If 10% was only 1,000, less than 1,000 respondents, that's very small group. Not even Tallahassee. Success failure condition. In the younger age group, 48 snored, 136 didn't. In the older group, all right, so those are all much more than 10. I know it seems really dumb to list all this out, but we have to prove this before we can continue. Okay, so you have to actually list this stuff when you do your free response questions. All right, because these conditions are satisfied, I'll use a normal model and perform a 2-proportion z-test. Again, write it just like this in your free response FRQs. All right, let's keep it going. So now let's do the actual statistics. So here we have our young, our old. We plug in our values. Okay, the observed difference in sample proportions is this. Here we can see our normal curve. We have it not being equal, remember. We're just seeing if there's any difference. We don't know if old or young, which one's going to snore more. So we do a two-tailed, and we get the p-value is really tiny. So then this is how we explain it. Okay? If there were really no difference in snoring rates between the two age groups, then the difference observed in the study would happen only 8 times in 10,000. This is so small that we reject the null hypothesis of no difference and conclude that there is a difference between older and younger adults. It appears that older adults are more likely to snore. Okay? That's what we would say. It appears. We don't say it is true. This is fact. Based on this study, we think this is true. All right, so let's do another example. If we go back to the online habits survey, so they were easy to find from their online profiles, while 28% of the boys said the same. Is there evidence between boys and girls? So let's perform a 2-proportion z-test. So give it a whirl. See if you can do it on your own. Okay, here you have your hypothesis. You have your conditions met. And here you have your statistics done. Okay, yes, you could do it by calculator, but you would have to list everything out. Okay, all in that test setting in your graphing calculator. Okay, but you have to name everything, just like in this last one where everything was named like this. You best believe you better do that if you're using your calculator. Okay, you got to identify what you're plugging into the calculator. Don't just say, I use the GDC and that's just it. Okay. All right, now in this example, we got less than 1%. So since that's very small, we reject the null hypothesis. So it's saying that there is a difference between the 2 proportions. Okay? So this is what can go wrong, so please be careful. Okay? You have to make sure that the samples are independent. Okay? You can't violate those independent issues. Okay? They must be random as well. A lot of times people just don't look for those things, okay, or overlook them because they just assume it's going to work out. Sometimes that's a question, and the answer is no, you can't continue. Okay, so don't just assume. Okay, don't interpret a significant difference in proportions casually. Okay, don't jump to conclusions about causality. All right, now this is what you've learned. Hopefully this all makes sense to you. If you've got any questions, just ask me in class. I'd be happy to go over anything.